As you can see here, we're finding the area under this curve. We've got this curve f of x equals x squared plus 1. And we've decided to break this range from 1 to 4 up into pieces, okay? Kind of like we looked at that other area before, and we were estimating the value by looking at, the squares that were in each piece and whatnot. The idea here, though, is that we can look at these individual pieces and we can approximate areas. In one way, we can do it with rectangles, okay? Now, you can see down here, we have two possibilities. We have upper rectangles and lower rectangles. And the difference is simply which side of the rectangle is hitting the function. The upper rectangle means that the higher value of x is the side that hits the actual function. Okay, so we have here, the right-hand side of the rectangle hits the function, so that would be the height of that rectangle. And then here, again, the right-hand side hits the function, and here the right-hand side hits the function. Okay, so you can see here, though, that this estimate has some limitations. Okay? What is going to be true about using this method here to estimate the area under this curve?
It'll be a little greater.
Yeah, it's going to be a little greater. It's going to be an overestimate of the area. As you can see here, it's going to include this and this and this. Okay? Now, I'm using the lower rectangles. Notice the left-hand side of the rectangle hits the function. But you'll notice here, this time we're going to get an underestimate because we're actually leaving out those little parts. Okay? Now, one idea to get a better estimate might be to average those two results. Okay, this one's going to be a little high, that one's going to be a little low. If we average the two, that might give us a better estimate. Okay? Another strategy that some might use would be to do something like this. Rather than make it upper or lower, make the height hit it right in the center. So in this case, we would be finding the height at 1.5. Okay, and then we'd come over here to 2.5 and hit the function there and make that the height of this rectangle. Okay? And then we'd come over here at 3.5 and make that the height of the rectangle. And you'll notice what happens with that is we actually end up kind of with two things happening. Here, we end up including some extra, but you'll notice we also end up leaving out some here, here, and here. And the reason why people would use this method is because the parts you're including kind of balance out the parts that you're leaving out. Okay? So this is about the same area. This is about the same area. This is about the same area. So you actually get a little better of an estimate. Okay? So this is a method of estimating area under a curve using rectangles. Okay? Now another way that we can improve this is to use more rectangles. Okay? You can see how much we're leaving out, using this, or I should say, in this case, how much we're including that we shouldn't. All right, this is all going to be extra if we did our rectangles like this. However, if we were to make twice as many rectangles, okay, check this out. If I made 2 rectangles out of that one, if I made 2 rectangles out of this one, notice I'm still using the right-hand side for the heights of my rectangles. Okay? Okay? So if I have that, notice at this point, I'm only including this much extra, and 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 this much extra. So notice, I've now cut out the little squares here that are only black. I've cut those parts out, so I'm including less extra. In other words, my overestimate is going to be not quite as much over as it was originally. Okay? If I were to do this again, let's say I cut each of those rectangles in half. Alright, so now I've got this rectangle here, this rectangle here, this rectangle here and here. Okay, I've got this rectangle and this rectangle. I've got this rectangle and this rectangle. Okay, got that. Got that. And we've got this. Okay, so notice I doubled the number of rectangles again, and this time though I'm only including that much extra area. Okay, so you'll notice I have even a less overage on my estimate. Okay, so in order to get the best estimate possible, what should I be doing?
As many rectangles as possible.
Divide it into as many rectangles as possible, because as you can see, each time we divide it into smaller rectangles, we lessen the amount of overage that we have. Okay?
So as that approaches infinity.
That's right. As the number of rectangles we have approaches infinity, our estimate is going to come closer and closer and closer to the actual area that we find, that we're looking for. Okay? Now, let me kind of illustrate this here. Using this one, we're going from 1 to 4. Okay? So let's let n be the number of rectangles. You guys know that the area of the rectangle equals length times width. Okay?
This is integration, right? That's what it's called.
We're going to be doing integration, yeah. Now, each of those rectangles is going to be part of that distance between 1 and 4. Okay? So if I do 4 minus 1, and then I divide it by the number of rectangles I have, that will give me the width of each of the rectangles. So if I want 20 rectangles, I have to do 3/20ths of a unit between as the width of each rectangle. Okay? Yeah.
What did you got 4 minus 1 and n? Like, is that a formula or?
I'm just thinking through here because I want to go from the area from 1 all the way to 4. So to find that distance, I'd subtract 4 minus 1.
And divide by the number of
Rectangles to figure out how wide each one would be. Okay? So that's my width. My length, or in this case, you could think of it as height, is going to be the y coordinate on the right-hand side. Okay? So the y coordinate on the right-hand side, if I'm starting at 1, I need to add this width a certain number of times, depending on which rectangle I want. So, for example, I would add this width once, and I would evaluate my function for it at that value to figure out the height of this first rectangle. Right? This would just be of the first rectangle. Okay?
Why is it 1 plus?
Because we're starting at 1, and I need to add the width to it. Okay? Then I evaluate the function there, and that'll tell me how tall that rectangle is. Okay? But again, that's only for the first one. Okay? So watch what I'm going to do here. The area of the first rectangle is going to be f of 1 plus 4 minus 1 over n times 4 minus 1 over n, length times width. That's only the first rectangle. In order to add up all of the rectangles, watch what we're going to do. I'm going to put this increment I in here, and we're going to add up from 1 to n rectangles. So the first rectangle, we're going to add that width once. The second rectangle, I'm going to get the x coordinate that I need to plug in by adding the width twice. That'll take me, here's adding it once. If I add it twice, that'll take me to this x coordinate. I plug it in, and that tells me how high that rectangle is. Okay? On the third one, I add 3 of those widths, plug it in, and that tells me how tall that rectangle is, and so on, until we get to n. Okay?
So what does I stand for?
I is just our increment, our counter in our sum. So the first rectangle, then the second, then the third, then the fourth, then the fifth, all the way up to n.
So we have to do that for every single rectangle and then add all of them up?
You would have to do that. And if we were in AP Calculus or Calc Honors, we would spend like a week doing these. All kinds of nasty ones. But thankfully we don't have to.
Oh.
Alright? Yes?
If you were to move that whole thing 5 over so that the very top, wait, no, it continues on forever, never mind.
Yeah.
What if you just wanted to find between -4 and 0?
Well, then you would just, instead of 4 minus 1, you'd do 0 minus a -4.
And then where would the 0 go?
Well, this one right here and right here would be the -4.
Plus.
And this would be 0 minus -4. This would be 0 minus -4. Okay?
Yeah.
We'll generalize this in a second. But earlier, I forget who said it, but they said we want the rectangles to get more and more and more rectangles. So we're going to let the number of rectangles approach infinity. So what are we taking there? If we want to find a value as the number of rectangles approaches infinity, we're taking a limit. Okay? So look at this. The limit as n approaches infinity of this sum is the area. Okay? And guys, this part right here, the limit of the sum is the integral. Okay? This is the integral. And notice we went from 1 to 4. So we would write it like this. The integral from 1 to 4 of f of x. Now notice f of x was the height, right? This was the height. F of whatever value we were working with. The width was this. It's the change in the x coordinate, right? That's the width of each rectangle. Well, instead of writing it like this, we write it as dx. Okay? So when we take an integral, we're really just taking the limit of a sum of the area of rectangles. The height times the width. F of x times d of x. Alright, that's all that is. A lot of people will try to just leave out that dx part. Okay? But don't. Make sure that you keep that dx part in there because that's the length times width part of our area of the rectangles.
And fx is what? It's y?
F of x is the height of each of those rectangles. Okay? So that's what's happening there behind the scenes, okay? And if we generalized all this, instead of just going from 1 to 4, if we went from A to B, that's what this would look like. Okay? Yeah?
So d of x is just the width?
dx is the width of those rectangles, yeah. And that's, if our number of rectangles is approaching infinity, what is dx approaching?
Negative infinity.
No?
Just kidding.
Just kidding.
If we keep dividing by more and more and more and more, it's going to approach 0. So those little slivers are approaching 0 width. Okay? That's why we've got to take the limit. Alright? So, okay. So I show you that because I just want you to understand what is going on here. We're talking about area. We approximate these with rectangles. And just a little notation here. I showed you this notation a second ago with the 1 to 4. But when we have a definite integral means we're finding area under a curve within a definite interval. Okay? Here it's between A and B. Okay? When we do that, we put a little a as a subscript, a b as a superscript here, so it's the integral from a to b of f of x dx. That's how we would read that. Okay?
So how do we find dx though? If that's the length and width?
Well, that's the nice thing of what we're doing, you don't have to. Okay? Yes. So, that's all I really wanted to deal with that, just to point out some of those things for you.